The new graduate certificate is a 15 credit certificate that you can achieve online. There's some key courses. One of the key courses is a graduate level course in IC engines. There's another class in thermodynamics of IC engines, and then there's several options to take. These courses are all available online and can be completed within 1 year. With that, I'm going to turn it over to Rick Davis, and he's going to present an excerpt from one of the courses where he's talking about abnormal SI combustion. Rick, you want to introduce yourself, and then we'll do a short snippet.
Yep, thank you, Jeff. Yep, my name is Rick Davis. I'm currently working for Michigan Tech for about the last 8 years or so. Prior to that, I was the Combustion Technical Fellow for General Motors, responsible for SI engine combustion system development processes for developing SI engines, and had a lot of experience in basic combustion, ignition systems, cam phasing, those kind of issues. So in today's topic, I'm going to switch to the presentation.
Next slides here, you Rick.
All right, so in today's session, we're going to talk about spark ignition engine knock. You hear it referred to as spark knock, N-gas auto ignition. Occasionally you hear it called detonation, which we'll cover here shortly. But to lead in, there's basically two main postulates that are out there in terms of what causes knock. One is N-gas auto ignition, and the other is detonation. And the terminology is a little bit confusing in the literature. So we go to the next slide. The first one we'll talk about is auto ignition theory. And basically, auto ignition, any combustible air fuel mixture, if you subject it to a high enough temperature for a long enough period of time, it will go through some precursor chemical reactions and auto ignite. And that can be tested in a setup like a rapid compression machine, where you can compress the mixture to a high temperature and pressure. And from that, you can record the auto ignition delay time for that given mixture, temperature, composition, and pressure. So in the auto ignition theory, as the flame is progressing across the combustion chamber, it is compressing and heating the N-gas, or the last mixture to burn on the far side of the combustion chamber. And it compresses that to a high enough temperature and pressure that that mixture can then self-ignite or auto-ignite. That auto-ignition results in, because it's gone through these precursor chemical reactions, results in a very rapid heat release rate in that N-gas, and that ends up creating a very high localized pressure that we end up hearing or determining as knock. So next slide. The other theory out there is detonation theory, and this is fundamentally different. This says that under knocking conditions, the conditions, again, mixture concentration, temperature, and pressure are such in the combustion chamber that the advancing flame front will accelerate to basically sonic and supersonic velocities, and then consume the remaining mixture at a much faster pace than the normal flame speed, which would result in the same kind of rapid heat release and pressure spike. And that theory has led many to call knock by the term detonation. There have been a lot of photographic studies, simulation studies, and things over the years that have shown that typical SI engine knock is really N-gas auto ignition and not detonation. So detonation is a real thing, comes into play in terms of explosives and those kind of things, but generally it's not supported by the studies as the fundamental cause of knock. There are some cases in a later part of the course, we'll talk about stochastic pre-ignition and super knock, which is a more recent phenomenon in boosted engines. And in those cases, there is some evidence that we are seeing developing detonation. But for normal SI combustion, it's really N-gas auto ignition. If you go to the next slide, this kind of shows what we're talking about. This is a optical engine still photograph taken of a combustion process. In this particular image, the burned gas is the darker region, and the lighter colored is the unburned or N-gas portion of the charge. And you can see the spark plugs down in the kind of 4 o'clock position, the flame initiated there, it's moving its way across the combustion chamber, and out in front of that propagating flame, you see some dark patches that show up, and those are auto ignition sites. So this is the start of the knock event on this particular cycle. The next slide. This is another study that's kind of showing, again, N-gas auto ignition. So the top portion of the slide is kind of a normal combustion event. Again, the flame is propagating its way across the combustion chamber from bottom right, to top left. And the bottom is a knocking cycle. And it's a colored version of that image. But the blue area here is the burn gas. So again, it's starting at the bottom right, moving its way up across the combustion chamber. And in frame G, you can again see that auto ignition start in the N gas region. So you see that blue region, and then you can see that the heat release rate there is extremely fast and generates a high amplitude knock. And we'll cover kind of the oscillation that we see here in a second. So if you go to the next slide. So this explains, when we talk about knock, what we're typically referring to is the associated noise that we hear. So the engine makes a pinging or a knocking sound when this occurs. And the reason for that has to do with what we term acoustic expansion. So in normal SI combustion, the heat release rate is slow enough that the pressure in the chamber is basically uniform. So you're releasing energy at the local flame front, which increases the pressure and decreases the density of that charge, but there's enough time for mass flow to occur to basically keep the pressure in the system in the chamber uniform. Under knocking conditions, the heat release rate is fast enough that there's not time for that acoustic expansion to occur. And so you actually end up with a very high pressure spike locally where the N gas auto ignition occurs. And that ends up setting up oscillating pressure waves across the combustion chamber that induces mechanical vibration in the engine structure. And that mechanical vibration is what we hear as knock. So if you go to the next slide. So why do we care about knock? And basically there's two folds here. One is it's basically an audible system that the customer has come to associate with noises the engine shouldn't make. So it's kind of an audible customer annoyance. And that kind of varies by region. In the United States in particular, we've come to associate that definitely with abnormal combustion. In other parts of the world where fuel prices have been extremely high compared to the US, for example, the customer base will tolerate a little bit more knock because the engine's running a little more efficiently under those conditions. So a minor level of knock is really not a structural concern per se, but if knock goes on undetected and unmitigated, then we can run into issues. And that's prominently because when knock occurs, it ends up with these high pressure oscillations in the chamber. Those increase the local heat transfer coefficients, and you end up with putting a lot more thermal energy into the combustion chamber surfaces, including the piston. If that continues over many cycles, it can increase the temperature of the components, reducing their mechanical property, and that can lead to piston damage. And if those surfaces get too hot, they can also lead to a runaway pre-ignition phenomenon. So a single episode of knock is not necessarily a big deal, but we don't want it to occur continually. So next slide. So when we talk about knock and this auto ignition phenomenon, there's both a temperature and a time component to that. So at very low engine speeds, when the engine's lugging, for example, in a high gear going up a grade, the N gas gets exposed to that elevated temperature for a longer period of time because of the slower engine speed. So it tends to be a time-induced phenomenon. And at high engine speeds, there's less time for that to occur. But because the higher rate of power output through the engine, the in-cylinder temperatures increase, and it becomes a temperature-driven phenomenon. And the knock sensitivity, if you look at the underlying equations that drive it, there's basically an exponential relationship to temperature. So increases in the thermal environment can lead to a much more rapid onset of knock. So the next slide. This shows a little bit of an indication of how knock is typically detected. So again, what we're detecting is not necessarily the underlying heat release that occurs, but we're detecting the mechanical vibrations or the pressure oscillations that occur. So this is an example of an in-cylinder pressure measurement. The left-hand side is the raw cylinder pressure versus time. And on the right-hand side, that signal has been basically low-pass filtered. So we took out the low-speed combustion event, and we're looking just at the high-frequency oscillations. And what you see is the there's very little high frequency contact up to a point, and then you see this large oscillation in the pressure spike due to the auto ignition, and that eventually just decays as the pressure waves die out in the combustion chamber. So that's a typical knock signal. Most modern vehicles use an accelerometer that's picking up mechanical vibration, and it sees a very similar trace, and that signal from the accelerometer is then filtered again to look at these high frequency contents.